Okay, today we're going to finish up Unit 8 concepts, including word and formula equations, as well as using the activity series. The main thing to remember when you're converting from words to formulas is just to break each section down of words and think about what it could translate to using your periodic table and your polyatomic element chart or ion chart. And also, one more thing to keep in mind is your Brinkelhoff elements. So I'm going to write that down. These are the elements that if they are not combined with something else, then they will not exist alone. So they will combine one of those with one of another element just like itself. So you'll never see just N all by itself, or hydrogen all by itself, or fluorine all by itself. They'll always either be a diatomic, which means there'll be two of them, or bonded with another element. Okay, so let's do a couple of examples. Now let's start down here. Copper 1 metal. Okay, so we can write that down as copper, metal, reacts with, which means it's going to be added to, aqueous silver nitrate. So we've got silver and we've got nitrate. This we found from the periodic table, this we found from the polyatomic chart. But this silver 1 means that silver has an oxidation of +1, so he's going to give away an electron. If you look at nitrate on the polyatomic chart, he accepts an electron, so they're balanced. So you just need one of each. And it says it's aqueous. To produce solid silver metal and aqueous copper 1 nitrate. Now, again, we're going to look at copper +2. Copper has a +2. Nitrate is going to take 1. So when you look at this, it's going to crisscross and you will get 1 copper, but you need 2 nitrates so that your electrons are all accounted for. Remember, copper +2 means it's giving away 2 electrons to be more stable, have an electron configuration like a noble gas. A nitrate is only going to take 1 electron, so in order for copper to give away both of those, he needs 2 nitrates. Okay, and it says aqueous, so we'll use our aqueous over here. Now it's time to balance using coefficients. You have 2 nitrates on this side, so I'm going to put a 2 up here because that will take care of 2 nitrates. But that means now you have 2 silvers, so we'll put a 2 in front of the silver. If you look at the coppers, they're both even, so you're done. Okay, let's do another one. Solid zinc metal reacts with aqueous copper. So solid zinc means you've got zinc, and reacts with means you're going to add it to aqueous copper 2 sulfate. So you've got copper 2, that's what the 2 means. Sulfate is on the periodic table polyatomic ion chart. Copper is going to give away 2 electrons, sulfate's going to take 2 electrons. They're equal, so you just need 1 of each. And it says it's aqueous. All right. To produce solid copper metal, so now you have copper as a solid, and aqueous zinc sulfate. Okay, so you've got a zinc and you've got sulfate, and it's aqueous, but now you need to figure out this bonding. Okay, so we're going to go back and we're going to look at zinc and sulfate. So zinc has an oxidation number of +1. He's going to give away 1 electron. Sulfate has a -2, which means he's going to take 2 electrons. When you crisscross, you need 2 zincs for every 1 sulfate for the electrons to all be accounted for. There can't be any left over or any extras or any missing. So let's go back and balance. You have 2 zincs over here, so I'm going to put 2 zincs up here so that they're balanced. 1 copper, 1 copper, 1 sulfate, 1 sulfate. Actually, you didn't need those little, I'm going to just rewrite that. just needed one of each. You didn't need the parentheses. Anyway, so there you go. You're balanced now. Okay. All right, let's move on down and talk about activity series. Okay, activity series has to do with whether or not a reaction will actually occur. So you'll need to have the handy activity series chart next to you when we're doing this to help you out. Basically, what you need to remember is that the more active metal will be in the bond. Okay? So if it's more active, it's going to end up in the bond, which means the less active metal will be alone. Okay? So let's look. If you look on your activity chart, you'll look between magnesium and zinc. Magnesium is a metal and zinc is a metal. Okay, so these are the two that are competing for the chlorine. When you look at those, you'll notice that magnesium is the more active metal. He's more active. Okay, if he's more active, then he gets to be in the bond. Well, he's already in the bond, so there won't be a reaction. Zinc cannot compete. All right, let's look at the next one, aluminum and water. You could rewrite water as H with OH, and what that means is that you have a hydrogen ion and a hydroxide ion. This is an acid, this is a base. That's how water is actually formed, even though we write it H2O. So when you're looking at this, aluminum is a metal or a cation, and he's competing with hydrogen. Now hydrogen is clearly not a metal, but he is a cation. So aluminum is either going to be bonded with hydroxide, or hydrogen is going to maintain its bond with hydroxide. So you look at the activity series, and you'll notice that aluminum is the more active of the two. Well, that means that aluminum gets to be in the bond. So let's look at aluminum, and you've got hydroxide, and guess who gets to go alone? Hydrogen. Okay, now a couple of things to look at here. First of all, aluminum and hydroxide do not necessarily bond in a 1-to-1 ratio. Okay, so aluminum has a +3 charge. If you look at the periodic table, that means that he's going to give away 3 electrons. Hydroxide only has a -1. So when you look at this and you crisscross to see how the electrons are going to go, you need 1 aluminum, but you actually need 3 hydroxide ions in order for this bond to occur, for all the electrons to be accounted for. So we'll need to rewrite this like this. Now let's look at hydrogen. Hydrogen is one of those Brinkelhoff elements. Okay. And the Brinkelhoff elements, remember, are never alone. They're either bonded with something different or they're bonded with another one of themselves. So hydrogen would be like this. Okay, now let's go back and balance. You've got, let's see, you've got 3 hydrogens over here plus 2 more makes 5. It's going to be kind of hard to balance a 5 over here. So I'm going to go ahead and even out this side so that I have even numbers of hydrogens. So if I have 2 times 3 is 6 hydrogens, okay, plus 2 more. Well, let's get our aluminum straight. Okay, we've got our aluminum, okay, but it's still not going to work out. Let's look at our oxygens. All right, it ends up being 6 over here, 2 here, and I've got 3. So if you look at everything, there's 2 aluminums. 6 times 2 is 12 hydrogens, and you have 6 here plus 6 more. 6 waters. 2 times 3 is 6 oxygens. So all of our chemicals are balanced. All right, let's clean this up a little bit. Let's do a couple of practices over here. All right, you've got bromine, which is a liquid, with potassium iodide. Okay, so this is an L, but this is an I. And know that looks a little confusing. But you notice about bromine, bromine's not a metal. Bromine is a nonmetal. Okay. So if it's a nonmetal, you cannot look at the activity series chart, because the activity series chart only shows you metals and hydrogen. So then how are you going to figure this out? Well, look at the periodic table. If you look at the periodic table, and this is a very rough drawing, fluorine is your most reactive nonmetal. The closer you are to fluorine, the more active you are as a nonmetal. Okay? And more active more active nonmetals, okay, they get to be in the bond because they're more active. All right, so is bromine or iodine closer to fluorine? Well, bromine is. So that means bromine's going to be in the bond. But you got to be careful about how you put the bond together. Bromine does not come first. Potassium is a cation and bromine is an anion, so you have to bond it in that way. Then you have iodine by itself. He's the one who is less active, so he gets to go home by himself. Now let's look at how this is bonded together. Potassium has a +1. Bromine has a -1. So when you crisscross those, you actually just need to have one of each. Look at iodine. Iodine is a Brinkelhoff, which means it cannot be alone. You're not going to have iodine by itself. Okay. Now let's talk about how to balance these. You notice there's 2 iodines over here. So there must be 2 iodines on this side. Gives you 2 potassiums. 2 potassiums. Now you have 2 bromines. 2 bromines. Now you're balanced. Okay, let's look at this next one. Gold and hydrochloric acid. Gold is a metal, so you're going to compare it to hydrogen because they're going to be competing over the nonmetal, chlorine. When you look on the periodic table, gold is more active than hydrogen. So hydrogen is more active than gold. So hydrogen is actually the winner. He's the more active one, which means he gets to be in the bond, so there will be no reaction, which means that the hydrogen will maintain its bond with chlorine and gold will not get to be in the bond because he's less active. All right, let's do another one here. Let's go over and do this one because this is another nonmetal. Okay, you have nonmetals. All right, iodine is a nonmetal and he will be competing with fluorine for potassium. So again, you're going to look at the periodic table and see which one is closest to fluorine. Well, gosh, fluorine is the closest. So fluorine gets to be in the bond. He's the more active one. So again, there'll be no reaction on this one. I hope that helps, and good luck.